So let us recall what we have did in the previous lecture. In the previous lecture, we have discussed about the limit of a function in a metric space. So for that, I required two matrices, that is x comma d1 and y will be x comma d2. And we have a function which is given as x to y. If I want to say that this function f has a limit a as x tends to a, which can be noted as fx is tending to L as x tends to a. For that, we have given epsilon greater than 0, there exists a delta greater than 0 such that d1 of x comma a less than delta implies d2 of fx comma L less than epsilon. With the help of this definition, we have discussed the properties of limit of a function. In that, we required this two function which are from x to r. They are the function which are real valued function defined over the metric space A. We required a point A which is in x and Lmn belongs to R. Then we can say that limit of a function, sum of the limit is the limit of the sum, that is m plus m, and the same result is for negative also. We have a product of limit is limit of product, that is L into m, and for the division also we have the same result. So with the help of this properties of limit and the definition of a limit, we have defined, that is next was the continuous function. So the continuous function, as I have already defined in the previous lecture, if you require this x comma d1 and x2 comma d2 are the two metric spaces, and a is belongs to x. If I want to say that f is function from x to y is continuous at the point a, since if the given epsilon greater than 0, there exists a delta greater than 0, d1 of x comma a less than delta implies d2 of f of x comma f of a less than epsilon. Or in the epsilon delta neighborhood definition, it can be written in this form, and it is noted or denoted in this way. Now with the help of this, we will have one important result, and that result is actually gives you the equivalent condition for the continuous function. So let us state the that result, that x and y be a metric spaces with metric d1 and d2 respectively. Let f be a mapping from x into y. Then prove that the following statements are equivalent. That means all the statements which I am writing here, they are same. The first one is f is continuous at x is equal to a. So I required a point A which is in x. The second, a given epsilon greater than 0, there exists a delta greater than 0 such that d1 of x comma a less than delta implies d2 of f of x comma f of a less than epsilon. This is equivalent statement because these two are the definition of the continuous function. The third one, it says that the inverse image of f of any open sphere s epsilon of f of a. So here epsilon is anything because it says that any open sphere of this about f of a contains an open sphere s delta of a about a. That means I can say for given epsilon greater than 0 or for every epsilon greater than 0 there exists a delta greater than 0 such that S delta of A, which is a subset of F inverse of S epsilon of F of A. So it says that inverse image of F of any open sphere. So inverse image of this open sphere that is represented in this way contains an open sphere of this. So this contains open sphere of A. And the fourth condition, it says that whenever xn is a sequence of points in X converging to A, then the sequence f of xn of points in Y converging to f of A. That means xn converges to A implies f of xn converges to f of A. Ultimately, what is this says that under the continuous function, the convergence is preserved. That means if xn is converged to A, we can say that f of xn is also converged to f of A. Now, to prove that these four statements are equivalent. Okay, so what I will do is I will prove that one is implies two is one is if and only if three, one is if and only if four. One is if and only if two, it is obvious because this is the definition of this continuous function. So we are not going to do anything with this first statement and the second statement. So the first I will start to prove that f is continuous, then if and only if the third statement is true. So let us try to prove that one. So let us assume that f is continuous at A. So by definition, therefore, for every given epsilon greater than 0, there exists a delta greater than 0 such that d1 of f xa less than delta implies d2 of f of x f of a less than epsilon. How we can write down this is in the neighborhood way. That means for every epsilon greater than 0, there exists a delta greater than 0 such that. What does that mean of this? It means that it is in the neighborhood of delta. So it says that A is belongs to, oh sorry, every X is belongs to a neighborhood of S delta of A, which implies, so whenever this, it is in this neighborhood, which implies f of x, it is in the neighborhood of S epsilon of f of A. So it is equivalent to write down the same thing. So therefore I can write down for every epsilon greater than 0, there exists a delta greater than 0 such that this statement I can write down, that is x is belongs to S delta of A, implies x is belongs to f inverse of S epsilon of f of A. So hence we got that inverse image of every point, or every point is in image. So whenever this is in this, so I can say that for every epsilon greater than 0, there exists a delta greater than 0 such that S delta of A is a subset of F inverse of S epsilon F of A. So that is our objective, is to prove to the first statement, that is the 1 is implies 3. So I should write here 1. I'm proving that 1 is implies 3. So that means we can say that the inverse image of any open sphere, that is S epsilon of f of A, about A, f of A, contains an open sphere S delta A about A. So that completes the 1 implies 3. Now we'll prove a 3 implies 1. So this is the proof of 3 implies 1. So what is the statement 3? It says that for every epsilon greater than 0, there exists a delta greater than 0 such that S delta of A is a subset of F inverse of S epsilon of f of A. So this is equivalent to write down f of S delta of A is subset of S epsilon of f of A. If I apply inverse both sides, and I will call this as statement 1. What we have to prove? We have to prove that this thing, that means whenever this is there, it will implies this, or ultimately I have to prove that if x is belongs to S delta of A, which implies f of x is belongs to S epsilon of f of A. This is objective is over. So I will start with one point in this, that is S delta of A, and we prove that the image of that point, that is f of x, will be in this neighborhood. So now when x is belongs to S delta of A, so this will implies f of x is belongs to f of S delta of A. So due to 1, we can say that f of x is belongs to S epsilon of f of A. This is because of 1. So ultimately what we can say is the distance between f of x and f of A is less than epsilon. When, what is the meaning of this? Is distance between, so this is a D2 norm, this is D1 norm. X and A is less than delta. So therefore we can say that f is continuous at x is equal to A. So this will prove the 3 implies 1. Now what we'll do is we'll prove that 1 is implies 4, and conversely next we'll prove that the 4 is implies 1. So to prove that one, so first I will prove the 1 implies 4. So let f be a continuous at x is equal to a, and xn is converse to a as n tends to infinity. This is also given to us because the statement was it is whenever xn is a sequence which is in x conversing to a. So that sequence I have taken, xn is belongs to a. What to prove? We have to prove that f of xn is converse to f of a as n tends to infinity. So this is our objective. So what is the definition of convergent sequences? So it is sufficient to prove that for given epsilon greater than 0, there exists n0 belongs to n such that I can say mode of or d2 of f of xn comma f of a is less than epsilon when n is greater than or equal to n0. So this is equivalent to right. That means f of x n is belongs to s epsilon of f of a whenever n is greater than or equal to n0. So this same definition I can write down in terms of epsilon neighborhood definition. So we have given that f is continuous at the point x is equal to a. So as f is continuous at a, we'll say that there exists a delta greater than 0. Epsilon is given, so I'm just using the same epsilon here. So delta greater than 0 such that fx is belongs to s epsilon of f of a whenever x is belongs to s delta of f of a. That is by definition of the continuous function. So ultimately what we can say from this definition, we say that for given epsilon greater than 0, there exists a delta greater than 0 such that S delta of A is a subset of F inverse of S epsilon of F of A. So this will gives you, therefore, for every epsilon greater than 0, there exists a delta greater than 0 such that F of S delta of F of A is subset of S epsilon of F of A. Also given that xn is converse to A as n tends to infinity, we'll take for every epsilon greater than 0, we can say that for every epsilon greater than 0, there exists n0 belongs to n such that xn is belongs to s epsilon of f of a for every n greater than or equal to n0. So take this epsilon is equal to delta. So we'll take this epsilon is equal to delta, which is greater than 0. So we can say that xn is belongs to S delta of A whenever n is greater than or equal to n0. So if I call this is the statement 1, then I want to apply f both the side. So this is f is belongs to f of xn is belongs to S delta of A for every n greater than or equal to n0. So this will implies due to 1, f of xn is belongs to S epsilon f of A whenever n is greater than or equal to n0. This is because of 1. So ultimately what I write here, that we want to sufficient to prove this xn, f of xn is belongs to S epsilon of f of A, that we have proved here. So we can say that therefore f of xn is converse to f of A as n tends to infinity. So that's complete the proof of 1 is implies 4. Next, we'll prove that 4 implies 1. That means suppose that xn is converse to A as n tends to infinity, implies f of xn is converse to f of A as n tends to infinity. That means under this map, every conversion sequence is preserved. So to prove, what to prove here is f is continuous at point x equal to A. Suppose not. Suppose assume that f is not continuous at x is equal to A. So these are the many ways to prove this statement. So I'm proving this statement by negation statement. That means not continuous. If it is not continuous, then by previous result, that means 1 is if and only if 3, we can say that what will be the negation of this statement? It says that for the inverse image of f of any open sphere about f of A contains an open sphere S delta of f of A. That means for every epsilon greater than 0, there exists a delta such that this condition is satisfied. So the negation of this statement says that instead of for every, there is some epsilon greater than 0, this condition will not be satisfied. Okay, so that is statement we should write. If it is not continuous, the inverse image of f of S epsilon of f of A does not contains any open sphere about A. That is the negation of that statement. So in particular, I am taking delta is equal to 1 by n. So what we can say is f inverse of S epsilon of f of A does not contains S1 by n f of A for any n belongs to n. So for any 1 by n, this will not be true. Therefore, for each positive integer, what will happen? Integer n, there is a point xn belongs to S1 by n A, because we have given that xn is converse to A, so this is already happened, such that f of xn does not belongs to S epsilon of f of A. Because of this, we can say this. And hence, what will happen is d1 of xn comma A will be less than 1 by n, but d2 of f of xn comma f of A is greater than epsilon due to this statement, we can say, which is a contradiction with xn is converse to A. Implies f of xn is converse to f of A. So that means what we have assumed that f is continuous, sorry, not continuous, will not be true. So therefore f is continuous at x is equal to A. So it will complete that this four statement are equivalent statements. And whenever we required, we'll use any of this statement to prove something is continuous or not. So let us discuss the next result, which is also based on the continuous function. And it says that the composition of a two continuous function is continuous. So let x comma d1, x1 comma d1, x2 comma d2, and x3 comma d3 are metric spaces. Let f be a function from x1 to x2, g be a function from x2 to x3. If f is continuous at point xa, which is in x1, and g is continuous at point f of a, which is in x2, then prove that GOF is continuous at point A, which is, so it is the x is from x1 is from f is from x1 to x2, and g is from x2 to x3. So GOF is defined. So it says that the composition of a two continuous function is continuous. And this is easy to prove, actually, this statement, which tells you that by definition, sequential definition, which we have discussed just now, that is, let xn be a sequence in x such that xn is converse to A as n tends to infinity. What to show? That is GOF xn converse to GOF at A as n tends to infinity. This is our objective. Since f is continuous, which is given at point A, so we can say by that result that f of xn converges to f of a as n tends to infinity. Since g is continuous at x is equal to a, we can say that g o f xn converges to g o f of a as n tends to infinity, and that completes the proof of this, that xn converges to a implies GOF is converges to xn converges to GOF at a as n tends to infinity. That means composition of a two continuous function is continuous. Therefore, GOF is continuous at x is equal to a. The next definition is a continuous function on x. So when we can say that a function on continuous on x, let x and y be a metric spaces with f, which is from x to y, is, or let f is said to be a continuous function on x if it is continuous at each point of x. So if it is continuous on x, it has to be continuous for each and every point in that set. As we have discussed the properties of limit, that a limit of sum is equal to sum of limit, product of limit is limit of product, and for division and for subtraction is also that same kind of result. Using that result, we can state one result, and we'll not discuss the proof. I'm giving you as a homework to do that. So we can say that if f and g are continuous real valued function on a metric space x, then prove that f plus g, f minus g, f into g, f divided by g if g is not equal to 0 are continuous on x. So this is, I'm giving you as a homework to do by yourself. You can prove this statement your, so this is the proof is homework. The next one, or I can say next example, is let f and g be a continuous function defined from R to R. So it is a real valued function from R to R. And let us define some function h, which is from R square to R, as h of xy is equal to fx comma gy for every xy belongs to R square. Then prove that h is continuous on R square. So here, using the function from R to R, we have defined one function which is from R square to R square, which is defined as this fx comma gx. So now we'll to prove this or to make a solution for this. There are many ways to do the solution for this. You can use any of the definition which we have discussed earlier. That means 4 equivalent condition we have seen. Any of that condition you can use to prove this. So I will use the definition or the equivalent condition which is about the sequence, that is xn converges to a implies f of xn converges to f of a. So here I want to show that x is continuous on R square. So it is sufficient to prove that. So we shall show that if xn yn, because now we have to take the sequence in this space R square, which converges to xy in R square, then how to prove that f of xn comma yn will converge to f of x comma y as n tends to infinity in R square, that means in codomain. So here what is given is xn comma yn is converged to xy as n tends to infinity. So can we say that this xn is converged to x and yn is converged to y? See here, what is the metric is a usual metric we are talking about. So therefore, we can say that xn is converged to x and yn is converged to y as n tends to infinity with usual metric, we can say. Why we can say that this one? Because what does it mean of this? The meaning of this one is for every given epsilon greater than 0 there exists n0 belongs to n such that mode of xn comma yn minus x comma y less than epsilon for every n greater than or equal to n0. But what is the meaning of this modulus? It means that the square root of xn minus x0 square plus yn minus y0 square is less than epsilon for every n greater than or equal to n0. But what does it mean of this square root? Can I say that it is xn minus x0 is less than this quantity, and similarly yn minus y0 is mode of that is less than this quantity. So we can say that for every given epsilon greater than 0 there exists n0 such that mode of xn minus y0 is less than epsilon and mode of xn minus x is less than epsilon for every n greater than or equal to 0. So we'll have this that we can say. And what is given that f and g are continuous on R, which is we have given this statement, that is f and g are continuous defined over from x to x, R to R. So it is continuous on R. So by property of this continuous function, that is xn is converged to x as n tends to infinity, and g of yn is converged to g of y as n tends to infinity. That proves this. Now we have to prove that f of xn, f of yn is converged to f of x, f of y. So what does it mean of this? Let us write. Therefore, for given epsilon greater than 0, there exists n0 belongs to n such that mode of f of xn minus f of x is less than epsilon, and mode of g of xn yn minus g of y is less than epsilon for every n greater than or equal to 0. See, in the for f and for g, there are different n0 is there, but I will take this n0 as a maximum of that n1 and n2. So that's why this will have n0. If you want, you can use this n1 here, n2 here, and here you will write n1 and 2. So what is next we'll do is we'll take this n0 will be the maximum of this n1 and 2. That will work. N0 is also here, so no problem if you write these two steps. So take this n0 is equal to this. Now what is d2 of f of xn comma yn, f of x comma y. So I want to prove that this is less than epsilon whenever n is greater than or equal to n0. But what is the meaning of this one? It says that as per the usual metric, this is f of xn minus f of x square plus g of yn minus g of y square. So this is less than under root of, to adjust this epsilon, we'll write down this is epsilon by 2, because here is epsilon by 2 come. So this is epsilon by 2 square plus epsilon by 2 square. But this will gives you epsilon square by 4. So still need to adjust something. Okay, no problem. So this is epsilon square by 2 is left. So that's why it is epsilon by square root of 2. And epsilon by square root of 2 is always less than epsilon. So whenever n is greater than or equal to n0, this inequality will be true for whenever n is greater than or equal to n0. So for every n greater than or equal to 0, we have this. So we can say that this will be implies epsilon. So hence we can say that therefore h of xn comma yn converges to h of xy as n tends to infinity, and this x comma y belongs to R square is arbitrary point as we can say that h is continuous on R square. So that completes the proof or solution for that example. Let us discuss the next example regarding the same, that if A is a subset of X where X comma D is a metric space, that means A is a subset of a metric space. Let us define some function f from x to r as f of x is equal to d of ax. That means I am defining a function which is from a point to set a set, and this function is a continuous function. That is our objective. For every x belongs to x, then prove that this f is continuous on x. So to prove this one, we have to prove that this has to be continuous at some point. So let us consider this point P. Let P is belongs to X. We will show that F is continuous point P. So for that, what I will do is I will fix this Q belongs to X. What we have, we observe something. That means by triangle inequality, we have d of Px is less than or equal to d of Pq plus Qp. This is you will get by triangle inequality, and this will gives you d of Xp is less than or equal to d of Pq plus d of Xq. Now, why I required this one? Because I want to prove that f of P minus f of Q. I want to prove that this is less than epsilon. So what is f of P is this quantity, and what is f of Q is this quantity. If I take over the infimum over X, so that's why I'm taking the infimum over all the points of X in A, we get d of X comma P is less than or equal to d of PQ because it is independent of PQ plus d of AQ. So this will gives you, therefore, d of AP minus d of AQ is less than or equal to distance between PQ. So therefore, this will gives you f of P minus f of Q is less than or equal to distance between PQ, and I call it this statement as 1. Similarly, one can also prove that f of Q minus f of P is less than or equal to distance between PQ. In the same manner as we have did here. That means I have started with Px, you can start with Qx, d of Qx, and then you use this triangle inequality and we can have this statement. So from 1 and 2, what we can say, that mode of f of P minus f of Q is less than or equal to distance between PQ. So whenever this positive or negative is not make any difference. So from this equation 3 we can say now, therefore from equation 3 we say that for given epsilon greater than 0 there exists a delta greater than 0 such that mode of f of P minus f of Q is less than epsilon whenever distance between PQ is less than delta. Or I can say the distance between PQ is less than delta implies this, due to this. Where what is your delta? Delta is exactly the epsilon that I have taken. So we can have f is continuous at point P, and therefore f is continuous on X, and which proves that statement. Now I'm giving you two examples to work by yourself. That means giving you two examples here. The first one, let f be a function, or I can say just define function. Define a function f from r square to r as f of xy is equal to x. This is known as a projection function because you are projecting your xy coordinates to x axis. Then prove that f is continuous on R square. This is defined for every xy belongs to R square. This I am giving you as a homework to do. The hint is this example. This example we have did here. Use the things which we have used in this example. So instead of here h of xy, we have proved that it is x fx gx. Here I have a projected on only x. So similar argument will be used to prove this one. Okay. One can also generalize this statement for n-dimensional space. That means define a function g from Rn to R as f of x1, x2 up to xn is equal to xi, where I, so I can say f of xi. So I is running from 1 to up to n. So there are, so we should write down here is fi. So fi's are the map from Rn to R, which defined like this for any x1, x2 up to xn belongs to R. Ren. Then prove that f is fi for each I. For each I, these fi's are continuous on R square. So with this, we'll stop here for today. So in this lecture, I have talked about the continuous function and some properties of related to it. If you have any question, you can ask.